Let's investigate the Pauli matrices. These matrices are very useful for describing many systems in quantum mechanics. I will begin by introducing some standard notation for the basis vectors of a two-dimensional Hilbert space. We're going to use the matrix representations of these basis vectors to construct the Pauli matrices. I'm going to use Dirac notation. So first, let me write down one of these basis vectors. The first basis vector that I'm going to write down is going to be labeled by 0. We're going to call this the ket labeled by 0. So this is a ket in Dirac notation. I'm also going to write down the matrix representation of this basis vector. And it is a column vector that looks like this. We have the entries 1, 0. So this matrix over here is just a representation of this vector. And this vector is an element of the two-dimensional Hilbert space. Now let me write down the other basis vector, which I'm going to label by 1. So I'm going to put 1 inside this ket. So this is the 1 vector. And the matrix representation that I'm going to have over here is going to be 0, 1. So this is also a column vector. Now this equal sign may be a bit deceptive because these guys are not actually equal to each other. This is just a matrix representation of this state over here. It's a matrix representation in a particular basis. And later in the video, we're going to see what basis this is actually being represented in. So this is the standard notation that we're going to use. We have the 0 state and the 1 state. You can think of this as a ground state and an excited state. That is a more familiar language when we're talking about a harmonic oscillator. So you could actually use this to describe the ground state and the first excited state of the quantum harmonic oscillator. You just have to ignore all of the higher excited states. There are many physical systems that can be described using this type of notation. And all those physical systems are described by a two-dimensional Hilbert space. So because this Hilbert space is two-dimensional, only 2 basis vectors are required. So these 2 basis vectors can be combined together in a linear combination, and you can produce any state that is an element of this Hilbert space. So these 2 vectors span the entire vector space. That is the language of linear algebra. Now, because we're using Dirac notation, it is very convenient to write down the kets. We can also write down the bras. So then we'll have bras and kets. Let's write down the bra versions of these vectors over here. So the bra version of 0 looks like this. We have the bra version of 0. And the matrix representation is going to be the Hermitian adjoint. So we have to take the transpose and we have to complex conjugate. Complex conjugation is not going to have any effect on these matrices over here because all of the entries are real. So the Hermitian adjoint is just going to be the transpose in this special case. So the transpose is going to look like this. We're going to have 1 followed by 0. Now let's do the bra version of 1. So the bra version of this guy over here. That's going to be the bra labeled by 1, and that's equal to the row vector 0, 1. So you can see that this is just the transpose of this vector. We have column vectors that represent these kets and row vectors that represent these bras. And you can also, when you're writing down these vectors, you can use different bracket styles as well. And sometimes people like to put commas over here to distinguish these guys, so they're not mixed up as a single entry. One more thing that I want to write down is the fact that these basis vectors form an orthonormal basis. So they're not just basis vectors which span the entire Hilbert space, they are also orthonormal. So they are mutually orthogonal and they are normalized. We can write that down in a very compact way. We can write this as the inner product of 2 of these basis vectors, which we can arbitrarily call J and K. That is equal to the Kronecker delta of J, K. So what does this actually mean? When we have a Bra-Ket combination, that is an inner product. This gives a complex number. In general, if you take the inner product of these two guys, you will get a complex number. Now the complex numbers are the field that we're using over here for this vector space. So if you think back to those vector space axioms in the previous videos in the quantum mechanics playlist, that is what we're talking about. And the field that we're interested in is the complex numbers. So the inner product combines these two vectors and it spits out a complex number. And in this special case, the complex number is just a real number. It's either 0 or 1. If j and k are not equal to each other, then this is going to give 0. So if these indices are not equal to each other, we're going to get 0. But if it's the same vector, if j equals k, then we get 1. And that is the normalization condition. So when this is equal to 1, we know that these are normalized. And when it's equal to 0, we know that they are mutually orthogonal. So that is a concise way of writing that orthonormal relationship. So this is the notation that I wanted to introduce. Now, one more thing that I also want to talk about is how we can take the inner product and the outer product. So over here we have a Bra-Ket combination, and we're also going to look at a Ket-Bra combination. First, let's write down an explicit example of this Bra-Ket notation. And I'll write this over here. So let's say we have a bra first. So I'm going to write a bra, and I'm going to put some arbitrary elements in here. And I'm going to complex conjugate them because we're taking the Hermitian adjoint. So this is a Hermitian adjoint of some column vector with entries a, b. And now let's take another vector with entries alpha and beta. So you can see that this is a ket and this is a bra. So we have a bra and a ket, and that's going to give us an inner product. So the way we would compute this inner product is by standard matrix multiplication. So that would give us A star alpha plus B star beta. So this is just standard matrix multiplication. We take this element, multiply by this element, and add it to this element multiplied by this element over here. So we just have to take the sum. And this is an element of the complex numbers. So that's a fancy C that denotes the complex numbers. So the important thing to remember here is that the conjugate transpose is on the left and the normal ket is on the right. But what if we swap this around? What if we put the ket first and then the bra? I'll write the result of that over here. So let's say we take the conjugate transpose of this and get it back to a ket. That's going to give us this column vector, A, B. And then we want a row vector that has been complex conjugated, and that's going to be alpha star beta star. So these are complex conjugated elements. Now, what is this going to give? This is not the inner product. This is a ket-bra combination. And the result of this is going to give a matrix. And in this case, it's going to be a 2 by 2 matrix. We're going to make a square matrix out of these two vectors. So that's going to look like this. We're going to have the form where the first element is going to be A times alpha star. The element over here is going to be A times beta star, A beta star. Then these two elements down here are going to be B times alpha star, and then B times beta star. So this is the 2 by 2 matrix that we get. And we can write this formally as an element of the matrices that are 2 by 2. I'm specifying the dimensions of the matrix over here. And the entries of this matrix are sourced from the complex numbers. So this is in general a complex valued matrix. And again, we're using that fancy C to denote the complex numbers. So you can see that when you have a Bra-Ket combination, that's very different to when you have a Ket-Bra combination. So an outer product over here and an inner product are completely different objects. And we're going to use this over here to construct matrices. And matrices are representations of operators in quantum mechanics. So we're going to get operators from this combination, and this is just going to give us values, complex values. So let's write down these matrices. Let's write down some interesting notation for these matrices. I'm going to start off with the identity matrix, which is sometimes grouped together with the Pauli matrices, but often it is excluded. So I'm going to use the notation sigma sub 0. Now, sigma sub 0 is equivalent to I with a subscript 2. So this is the 2 by 2 identity matrix. How am I going to write this? Well, I'm going to write this in the same way that we would write the completeness relation when we're talking about Hilbert spaces. We would take the Ket-Bra combinations of all the basis vectors and add them together. So first we need this 0 vector. We'll take the Ket and then the Bra, and then we add that to the Ket 1, then the Bra 1. So you can see that this is the completeness relation for a Hilbert space. We take all of the basis vectors, which in this case are just 2 basis vectors, and we take these Ket-Bra combinations and add them together. So if you take a general state, which is a linear combination of these 2 basis vectors, and you act with this operator on that state, it will have no effect. That is why this is called the identity operator. And if you take the matrix representations of these basis vectors over here, and you do this outer product, you will actually get the matrix that looks like this, the identity matrix, which has 1s on the diagonal and 0s on the off diagonal. So that's what we get. Now let's have a look at some interesting properties of this matrix. The determinant of this matrix is equal to 1, and specifically it is plus 1. So I'll write this as the determinant of sigma 0 is equal to plus 1. What about the trace? The trace of sigma 0 is equal to plus 2. Let's write a 2 over here. So the important thing to notice is that the trace, which is the sum of all of these diagonal elements, 1 plus 1, that is non-zero. So this trace is a positive number, which is 2. And this determinant over here is plus 1 for the identity. This is going to be different for the Pauli matrices, which we'll see in a moment. So the important thing that I want you to remember is that we have just used these matrix representations up here, and we've used this rule for the outer product. That's the Ket-Bra combination, and that's given us this matrix over here. And that is the completeness relation when we're talking about Hilbert spaces. So a Hilbert space is a vector space that satisfies all of the inner product space axioms, and it also has that completeness requirement. So this is that completeness requirement, which tells us that we're dealing with a Hilbert space. Now we have sigma 0, so the next one is going to be sigma 1. So I'll write sigma 1 underneath. Sigma 1 is also known as sigma x. This is the Pauli x operator. And it is written as 1, 0 in this outer product plus 0, 1. So you can see it's almost like this identity, but we've just swapped around the 0 and the 1 over here. So here we have 1, 0, and then we have 0, 1. What does that look like in the matrix representation? Well, it has 0s on the diagonal and 1s on the off diagonal. So it's a flipped version of this identity matrix. And the effect of this Pauli x operator on a state is to swap the 0s and the 1s. So it's kind of like a bit flip. It swaps states around. 0 goes to 1 and 1 goes to 0. So that's the effect of this operator. And you can see that now the trace is going to be 0. So 0 plus 0, these diagonal elements, they give 0. And the determinant is actually minus 1 in this case. And we'll see that in the other two cases as well. So let's write down the other two of the Pauli matrices. So this one is the Pauli x. We also have the Pauli y, which is sometimes denoted as sigma 2. So that's equivalent to sigma y. And that is equal to I times 1, 0 minus I times 0, 1. So we have the same Ket-Bra combinations as the Pauli x operator, but it's accompanied by these imaginary units. And it is possible to also have another convention where you flip the sign, but I'm going to use this convention where I comes first over here, and then we have minus I. So what does the matrix representation look like? Well, the matrix representation looks like this. We have zeros on the diagonal, and then we have plus I over here and minus I over here. So this bottom left entry over here, that corresponds to this. And it's exactly the same in the Pauli X operator. This 1-0 combination, that is this bottom left entry. And the 0-1 entry is this top right entry. When these labels are exactly the same, we're on the diagonal. So 0-0 and 1-1 sit on the diagonal. And you can see that 0-0 and 1-1 don't appear in Pauli X and in Pauli Y. That's why we have zeros over here and zeros over here. So the diagonals are 0. Let's define the final Pauli matrix, which is sigma 3. That's also known as the Pauli Z or Pauli Z matrix. So this is very similar to the identity. It has this 0-0 term, but it has a minus sign for the 1-1 term. So here we have a minus sign instead of a plus. So in the matrix representation, this looks like this. We have a 1 and then a minus 1 on the diagonal. And on the off diagonal, we have zeros. So this is also a diagonal matrix. Now, I want to write down some interesting properties that are shared between these three matrices over here. So I'll write this explicitly as we're going to use an index j. So let's write down for j equal to 1, 2, and 3, what are we going to have? Well, the determinant is going to be minus 1. All three of these matrices have a determinant of minus 1. So the determinant of sigma j is equal to minus 1. What about the trace? The trace is equal to 0 over here. We have 0 plus 0, 0 plus 0. And over here we have 1 minus 1, which is also 0. So the trace of sigma j is equal to 0. And another name for that is traceless. So these three matrices are traceless. But now let's consider including this identity operator over here. Let's consider all four of these matrices. So I'll write this underneath for all four of these guys. So for j equal to 0, 1, 2, and 3, there's an interesting property. All of these matrices are Hermitian. So that means sigma j with a dagger over here, the Hermitian adjoint, is equal to sigma j. So if we take the Hermitian adjoint, we get back the same matrix. And you can see that this is real valued and symmetric. This is real valued and symmetric. This one is real valued and symmetric. But this one is the only one that has imaginary components. We have an imaginary unit I and minus I over here. So if we take the transpose, this minus I will swap with this I. And then when we take the Hermitian conjugate, those guys will get negated and we'll get back the same matrix. Another interesting property is if you square one of these Pauli matrices, so if we take sigma j squared, it always gives back the identity, sigma 0. The identity squared gives back the identity, and squaring any of these guys, Pauli x and Pauli y and Pauli z, that will also give back the identity matrix. Now, I also want to talk about some other bases we could represent this system in. These are eigenbases. So we're actually dealing with the basis vectors of the Pauli z operator. So this 0 and 1, they're the basis vectors of the Pauli z operator. I'll write that over here. So the Pauli z operator is denoted, so let's write this as the eigenbasis of z with eigenvalue plus 1. That is the same as this 0 ket that we're using over here. And the eigenvector for the Pauli z operator with minus 1 is the same as this ket over here with a 1. So these two are the basis vectors that we're using to represent all of these matrices. But there are alternative eigenbases that we could use. We can use the eigenbasis for the Pauli x and the eigenbasis for the Pauli y. Let's see how we would do that. So I'll write that over here. Now, I'm using this notation with a little subscript plus and a subscript minus to denote the eigenvalue. The eigenvalues of these matrices, these three Pauli matrices over here, are either +1 or -1. That is one of the properties that you can deduce from the determinant and the trace that you know over here. So we have two eigenvectors that we can normalize, and we know that the eigenvalues are either +1 or -1. So we've already written down the z basis. This is the z eigenbasis, and it is normalized. We have these vectors are normalized, as we've written up here with the orthonormality condition. Now let's work out the basis vectors for this Pauli x operator. So I'll write them in one shot. So we'll have x plus or minus. So we're writing both of this eigenbasis. So plus corresponds to a +1 eigenvalue, and minus corresponds to a -1 eigenvalue. We can write this as the square root of 2 times a linear combination of 0, the 0 state, plus or minus the 1 state. And we can also write this in a vector form. We can write this as 1 over the square root of 2, that's just a normalization factor, times the column vector 1 plus or minus 1. So that's what we have over here. That is the eigenbasis for the Pauli x operator. Now let's write down the eigenbasis for the Pauli y operator, and I'll do that over here. So the Pauli y operator, which I'll write as y plus or minus in a ket, that is the linear combination. So we're also going to have a normalization coefficient of 1 over square root of 2. It's a linear combination of the 0 vector plus or minus I times this 1 vector. And we can write this as a matrix with a normalization coefficient 1 over the square root of 2. And then we're going to have 1 plus or minus I. So you can test this out, use standard matrix multiplication, try and apply the Pauli y operator to these two column vectors, and you will get eigenvalues of +1 and -1. So these are the alternative eigenbases, and it's very useful to use these eigenbases. Another property that I want to write down is if you consider all 4 of these guys, you can take them and you can turn them into basis vectors for another vector space. So if we, for a second, ignore the 2-dimensional Hilbert space, we can think of a 4-dimensional vector space where the vectors are actually matrices. So let me write down a general 2x2 matrix. I'll call that 2x2 matrix A sub 2. And this is an element of the matrices that are 2x2 and have complex entries. So just like what we were dealing with up here. So this is an example of such a matrix. So what we can do is we can take A2 and we can write it as a linear combination of, so I write this as a sum of j going from 0 to 3 of some coefficients alpha j times these matrices going from 0 to 3. So this is sigma j. So over here, we're going from 0 to 3. The only time we excluded this identity was in this red line over here. Here we explicitly stated that j went from 1, 2, and 3. So we have Pauli z, we have Pauli y, we have Pauli x, and we're also including sigma 0. So this linear combination has a bunch of these complex coefficients. Now let me write this out more explicitly. I can write this in a matrix notation. So I can write this as a 2x2 matrix. And on the diagonal, what I'm going to have is alpha 0 plus alpha 3, and then alpha 0 minus alpha 3. And on the off diagonal, I'm going to have alpha 1 plus I alpha 2, and then over here I'm going to have alpha 1 minus I alpha 2. So this is a 2x2 matrix. So where did this come from? Well, this just came from scaling each of these matrices by alpha 0, alpha 1, alpha 2, and alpha 3. And you can see that alpha 0, which is this identity matrix, that contributes this, and then we have a alpha 3 and a minus alpha 3 over here, also in the diagonal. And on the off diagonal, we have a combination of alpha 1 plus I alpha 2, that's this, and then over here we have alpha 1 minus I alpha 2. So we have to take the complex conjugate over here. But in general, these alphas are all complex numbers. So we can also write this as a column vector. So we can write this as a column vector with entries, write them in, I'll write them in black. So we have alpha 0, alpha 1, alpha 2, and alpha 3. So now this is a column vector with 4 entries. So we're writing this in the basis of these matrices. So this basis, which is also an orthonormal basis. But the inner product is not standard matrix multiplication. The inner product is very different. The inner product involves taking the trace. So let's define a new inner product. Let's define the inner product between two matrices, A and B, like this. The inner product is going to be 1/2 of the trace of the matrix product of A and the Hermitian adjoint of B. So this is the inner product that I'm using to define this new inner product space. So what we can do is we can actually find these alphas by taking this inner product. So let's evaluate, write this explicitly. These alpha j's can be found by taking 1/2 of the trace of this matrix A2 and taking the product with the specific associated value as the same j of this Pauli operator. So we have sigma j in here. I don't have to take the Hermitian adjoint because these operators over here, these matrices, are all Hermitian. So putting an extra cross over here or an extra dagger, that would be exactly the same. It wouldn't change anything. So this is how you would find the coefficients in this linear combination. And one final thing I want to write down is the orthonormality relationship. So these guys are orthonormal. So that means if we take 1/2 of the trace of the product of sigma j and sigma k, well, that's going to be the Kronecker delta of j with k. And I want you to keep in mind that all of these j's and k's over here, j's and k's, they all go from 0, 1, 2, and then 3. So this is the values that these j's and k's take on. So what is the reason for this 1/2? There's a factor of 1/2 in this definition. The reason that 1/2 is there is because of this trace. The trace of the identity matrix for the 2x2 identity matrix is 2. And this 2 needs to be factored away. We need to divide by that 2 so that we can normalize and we can get 1 from this inner product. So this over here is actually the inner product of 2 of these matrices from this set of 4 matrices over here. So what have we done in this video? We started with some Dirac notation for the basis vectors of a 2-dimensional Hilbert space. We defined some kets, we defined some bras. We also stated that this is an orthonormal basis set. Then we looked at inner products and outer products. We used outer products to construct the Pauli matrices and the identity matrix. We looked at the determinants and the traces of these matrices, and we found that the 3 Pauli matrices were traceless. They have a trace of 0, but the identity has a trace of 2. The identity has a determinant of +1, and all of these Pauli matrices have a determinant of -1. And we also looked at the eigenbases of the Pauli X operator and the Pauli Y operator. Everything else was written in terms of the eigenbasis of the Pauli Z operator. Then we took a linear combination of these 4 matrices, and we used them as basis vectors for a new vector space consisting of matrices. And these are 2x2 matrices with complex entries. We defined an inner product involving the trace, and this inner product can be used to show that these 4 matrices form an orthonormal basis. So we can actually write any one of these 2x2 matrices as a column vector, because this is a vector space. And it's also an inner product space because it's a vector space equipped with an inner product. And then we also use that inner product to find the coefficients in this linear combination. The Pauli matrices are frequently used in quantum mechanics. If you want to see more applications of the Pauli matrices, make sure you watch the other videos in the quantum mechanics playlist, which you can find over here.